talk about our assignment of control system. Our topic is temperature control system for a greenhouse. Our team consists of 3 persons, which is Navinesh Analaki Krishnan, Dineshwaran Analaki Anumandan, and Deva Prasad Analaki Sivalingam. So first of all, I'm going to explain about the system of temperature control system for greenhouse. The temperature control system for a greenhouse plays a crucial role in maintaining the optimal temperature environment necessary for the plant growth and productivity. Greenhouses provide a control setting where factors like temperature can be adjusted to create ideal conditions for plants. The objective of the temperature control system is to ensure that the condition of plants and the actual temperature inside the greenhouse closely matches the desired temperature set point. This is achieved through the use of sensors to monitor the temperature and actuators to adjust the heating and cooling mechanism.
For the first part, I will explain about the application of a greenhouse. A greenhouse is a structure that is used to grow plants in a controlled environment. The temperature in a greenhouse can be controlled using a second order system. The system consists of a sensor that measures the temperature inside the greenhouse, a controller that compares the measured temperature to desired temperature, and an actuator that controls the amount of heat or cold that is added to a greenhouse. Next, I will explain where the control system is being used. A temperature control system for a greenhouse uses feedback to maintain the temperature of a greenhouse at the desired level. The controller compares the measured temperature to desired temperature and then sends a signal to an actuator to adjust the amount of heat or cold that is added to the greenhouse. Now I will show you the block diagram for the application that we used. First, the desired temperature goes to a comparator, then through a regulator, heating system, after that control temperature, then finally to a temperature control.
Okay, this is our transfer function. So we use this to calculate our peak time, settling time, and the percentage overshoot. For the peak time, we got 0.4555. For the settling time, we got 2.668, and the percentage overshoot was 98.5%.
Now we will show you the comparison between calculation value and simulation value. First, the peak time of calculation is 0.55 and for the simulation is 0.61. The percentage of error between the calculation value and simulation is 34%. Next, the settling time for calculation value is 2.668 and for simulation is 5.1. And finally, the percentage overshoot for calculation value is 98.5% and for simulation is 61.7%. This is occur because of procedure error. This is the calculation for steady state error for step input, RAM input and parabolic input. For step input, the error is 0.9615. The error for RAM input is 25. And finally, the error for parabolic input is undefined due to the system not being able to perfectly track the input.
This is the step response we got from the simulation. For the peak time, we got this, and this is our rise time, this is the response, and this is the transient time, and this is our final value. Based on the project we done, we focus on the findings and implication of the analysis of the temperature control system for a greenhouse. The derived transfer function provide insight into the system behavior and dynamics, highlighting the presence of second order dynamics. Ensuring that all poles are in the left half of the complex plane indicates the system stability. Stable systems are desirable as they prevent oscillation and maintain reliable temperature control. The calculation of steady-state errors for different input signal such as step, ramp and parabolic inputs allowed for an assessment of the system tracking accuracy. Steady-state error represents the difference between the desired temperature set point and the actual temperature at equilibrium. Understanding the system ability to accurately track the desired set point is crucial for optimizing the control strategies. By comparing the calculation value and simulation value, there is a minor error due to human error and procedure error.
In this assignment, we have considered the application of a second order system to a temperature control system for a greenhouse. We have first explained the application, then drawn a block diagram of the system, and finally modeled the system to get the system transfer function. We have then calculated the peak time, settling time, percentage overshoot, and steady space representation of the system. Finally, we have discussed the stability of the system and calculated the steady-state error for step, ramp and parabolic inputs. We have also learned how to use MATLAB software not only for this assignment, also for real-time application.